It's a non-metal here, isn't it? All right, we have a picture. Okay, let's see if we can do this. We started off just looking at graduated cylinders and main volumes. We actually transferred some stuff out. I just wanted to go over the meniscus thing, make sure everybody got it. Here are just a couple. This is a small volume. This is a large one. With a small one here, first of all, you want to look at your meniscus. It's going to be at the very bottom. It's a negative meniscus, it's called. And it should be just about right there. Now, as we go to read this, remember this is 6, this is 7. So that's 0.2, 4.6, 0.8. So to me, it looks like it's more than 0.6, about 6.62, a little bit more than the 0.6 mark. With a small one like this, you can easily read it to 1/100th of a milliliter. Now what you were working with was a 100 mil graduated cylinder. Again, here's our meniscus. It's the negative meniscus. So we're right there. And if we were to read this, this is 50, 51, 52, that's 53. So it's just short of 53. I would do like 52.8 as a read. Meniscus come in both positive and negative. This is a negative meniscus. If you have mercury, mercury actually has a positive meniscus. So it caves up. With a mercury, you would read at the top of the meniscus. Water, you read at the bottom.
So if it caves down, then that's negative.
Right.
If it caves up, then it's positive.
That's right. Now, you had to do calculations for volume and whatever. Let's just go ahead and do a couple simple rounding exercises to make sure that we all understand the rules for rounding. If the digit you're going to remove is more than 5, preceding number increases by 1. So here we're going to round to 3 significant figures. So we're getting rid of the 9. So we have our 7 here. The digit removed is 9. So this goes up to 3/8. Very simple rounding rule. 3 significant figures. Removing the 9, so it goes up. The 7 goes to 8. If it's less than 5, you're going to do the opposite. So here we're going to round to these 3 significant figures. This is less than 5, so let's just say at 241. If the digit removed happens to be exactly 5, it depends on whether it's an odd or even number. So here we have 17.7, we're getting rid of our 5. 7 is odd. If it's odd, it rounds up. Here we're getting rid of our 5, but 6 is an even number. So instead of rounding up, this guy rounds down. If you think about it statistically, you're going to round up and down as many times, so it all works out. We're not going to actually do problems where I make you do this, but it's just good to know the rule. Any questions? You also did a bunch of measurements, and the little lab book talks about the accuracy of your measurement. I wanted to try to explain the difference between accuracy and precision. They're actually 2 different things. Precision refers to how reproducible a value is. So here we have a dartboard. We have tossed these darts in a manner that is neither precise nor accurate. They're all over the place. They're just scattered everywhere, right? Bad measurement, neither precise nor accurate. If we did this, we would have a pattern that was very precise. That is, they're all hitting the same spot here. But we're aiming for the bullseye, so we're not very accurate. So here's a measure, or here's an example of something that can be precise, but not accurate. If we do this, we have both precision and accuracy. Once again, the thing I want you to note is that a measurement can be very precise over here, but not accurate. Density, mass divided by volume. If you had 25 cubic centimeters of water, remember that's 25 mils, and you look it up at 25 degrees, the mass should be 24.9 grams, and that would give you a density, mass divided by volume, mass divided by volume, of 0.996. Now this is exactly what you look up. This means that this is a very accurate determination. If you did this 7 times and you got the same answer every time, it would also be a very precise answer. Another way to look at it is this way. Here we have, we're measuring a mass of water in grams, 25 mils. High precision, high accuracy, we do it 4 times. We wind up with data that are all clustered right around where they're supposed to be. High precision, high accuracy. If instead we got a bunch of data that were up here like around 27, but very highly reproducible, this would be very precise, but not accurate. Now, how does that happen? It could be that your balance was out of calibration, that your volumetric flask was wrong, something was wrong, so it's a systematic error. You can also do low precision work, but still wind up with the right answer. So here we're doing numbers that are all over the place, but if you take the numeric average, my gosh, it's right at 25. So low precision, high accuracy, and of course the final thing, low precision, low accuracy, you're just everywhere. Any questions? All right, we talked about density. Remember, density is mass per unit volume. Typically, it's expressed in grams and cubic centimeters. Remember that a liter is 1,000 cubic centimeters, and 1/1000th of that is called a milliliter, capital L at the end, and that these two are identical, milliliter and cubic centimeter. If we look at the example of gold, we have exactly 1 cubic centimeter of gold. Find that it weighs 19.3 grams. Density is simply the 19.3 divided by the volume, which is 1. And so that would be our density. Now what you did is measure something like this. And let's pretend that you got numbers that look something like this. A height of 1.2, a depth of 1.2, and about 5.4 centimeters. One of the things that I ask you to do is to calculate the volume of this. Now that's really simple because it's just length times width times height. Okay? All you do is plug these in. It doesn't matter which ones you choose, as long as you multiply them together. When we do all this, we get 7.776 cubic centimeters on our calculator. But remember that all of these measurements that you made are only good to 2 significant figures, aren't they? If they're only good to 2 significant figures, we have to round this to 2 figures. So this is going to round up to 7.8. All right, we take this bar and we weigh it. It turns out to be 73.0 grams. Let's take the volume we did on the previous slide and calculate its density. So we're going to plug in 73 grams for our mass. We have 7.8 cubic centimeters for our volume. We do our math on our calculator, and we get this number. How do we round that?
2 significant figures.
That's right, 2, because you look at that, this guy's 3, but this is still only 2. And you can't be any more accurate than your worst measurement. So we have to round this guy to 9.4.
But why did you use the second one? Because it has the centimeter, the thing right there, instead of using the one with the 3 significant figures?
Oh, whenever you do a calculation, you look at the significant figures in all of your numbers. And whichever one is the smallest, that wins. One other thing I'd like to point out about density. We said this and we did density. It's an inherent property of a substance. And that means it's independent of the size of your sample. Now let's say that you had one of the brass bars. And we did this calculation and we came up with density of 9.4 grams per cubic centimeter, right? We all understand how to do that. But what if instead of 1, we did 2 bars, 2 identical bars? So we weigh them both, comes up to 146. They both have exactly the same volume of 7.8, so that's 7.8 times 2. Calculate our density. Here's our mass, here's our volume, 2 times 7.8. Do this calculation, and by gosh, it turns out to be exactly the same. So it's independent of the size of your sample, an inherent property. Any questions? All right, let's go ahead and do the exam 1 review. Your actual exam will look very, very much like this. All the questions will be different. All the answers will be different, but it'll look the same. So you won't get the shock of looking at it and saying, oh my goodness. Our first question. We have a sample with a mass of 5.5 grams. What is this in milligrams? Well, these kind of things you really should be able to do in your head by now. We know that there are 1,000 milligrams in a gram out there. We know there are 1,000 grams in a kilogram. You can do that in your head. If we wanted to do it out the long way, we could take our given here, our 5.5 grams, our ratio, the ratio we would stick in. We know that there are 1,000 milligrams in every gram. So we simply say 1,000 milligrams in a gram. Now we set this up properly. Our grams are going to cancel. Only unit that's left is milligrams. So what's our answer? 5.5 times 10 to the third milligrams. And once again, doing it in your head, you would just read this and say, oh, 1,000 in every gram, so that's 5,500.
I can see.
Any questions? right, here's our table. Everybody will get a periodic table with their exam. But we'll use this one for right now. Or we'll use this one. We're looking at magnesium first. Step one, we have to find it. It's right here in group 2, third period, and has an atomic number of 12. Now remember what the atomic number is. That's the number of protons, right? Therefore, that's 12 protons. Now, in our table here, we say that this magnesium only has 10 electrons. So it has 10 negatives and 12 positives. So what's its charge? It's +2. And finally, if the mass number is 24, and 12 of those are protons, how many are neutrons? 12. Let's do lead. Lead is down here in the 6th period. It's over here in the 4th group. And it has an atomic number of 82. So, how many protons? 82 protons. Now, we're given that it has 125 neutrons. It has 82 protons. The mass number is simply the sum of these two. I can't do that in my head, but I could. It's about 207, isn't it? And finally, if this lead has a charge of +3,
247.
we have 82 positives. So how many negatives? To give us a +3, 79. Any questions?
Hang on. So, okay.
Can you go over that just one more time?
Okay,
The lead?
the last one?
Yeah.
All right, 82 protons, right?
Mm-hmm.
Mass number is protons plus neutrons, 207.
You said mass is protons plus neutrons?
Yep.
Yes. And whenever there's a positive charge, then you minus the electrons.
That's right, there are, that means there are more positives
What
than
is a
negatives.
positive charge?
Okay.
So you must only have 79 electrons
Minus electrons.
and 82
Minus for
protons.
electrons. Positive charge.
Very simple thing. Here's a fill in the blank for ammonium hydrogen carbonate. Now, ammonium was the only cationic polyatomic that we know. It's the derivative of ammonium. Ammonia is NH3. Ammonium is simply NH4. Now, carbonate, we remember, is a -2. It's CO3 minus 2, carbonate. CO3 minus 2. Well, let's put carbonate up here. But this is ammonium hydrogen carbonate. Remember, for hydrogen carbonate or hydrogen phosphate or whatever, all you do is insert one hydrogen here. It's actually bonded to one of these oxygens. And that is ammonium hydrogen carbonate. Now you'll have a question pretty much like this. So just make sure you know the basic, simple polyatomics. We're not going to do anything really fancy, just the basic, simple polyatomics.
Okay, can you explain to me really
Again?
quick how you
Yeah.
get ammonium for NH4?
Yeah.
It's the only positive one you have to remember in the entire course.
But how did you get NH? I don't understand.
Oh,
how
you have to remember that.
Oh, so
This is one of the
ammonium is
things
just
in life you
NH4.
just have to remember.
That's what you need to
Yeah.
That's what I was telling you. You have to remember the NH4.
Ammonium is earlier.
All right, we're looking for the atomic symbol of an anionic element. Charge of -2, 18 electrons, 16 neutrons. All right, well, let's look at our periodic table. Now, if it was a neutral element with 18 electrons, how many protons would it have?
16.
18, right.
18.
But this is anionic with a charge of -2. That means it has too many electrons. So
So
how many
it's-
protons would it have?
16.
16, right.
You know what I meant.
I know. So we simply look for atomic number of 16.
It's up.
But that's it.
Oh no.
S.
We're not going to die again, are we?
Oh,
Holy shit.
That will be in the video.
It'll be in the video.
And I'm gonna listen to that and replay. That's awesome.
That was funny.
Oh my gosh.
I've never heard him. I can't even picture him.
I know.
All right, well, let's see. All right, we got our periodic table. We're looking for 16 protons, so we're dealing here with sulfur. Okay? That's good. Now, that means that we want the atomic symbol. We start off with the symbol for the element. We are going to put the number of protons as a subscript. We will put the mass number as the superscript. Now, we're given that this has 16 neutrons. We know it has 16 protons, so that's 32. Finally, we have to show the charge. And we just do that as either 2 minus or minus 2. The thing to remember in this problem is because it has a charge of -2, there are too many electrons, and that's how we know it has 16 protons. Very simple density calculation straight off the tutorial. I hope you've done it. We're looking for mass. We know that density is mass divided by volume. So we simply solve that for mass. Mass is density multiplied by volume. So all we have to do is take our density and our volume, multiply them together, and we get 9.84.
And you said you're not going to put anything where we got a round, are you?
Well, you might have to round, but you're not going to have to round the 5.
Oh.
So remember the 5 rule.
Okay.
You don't have to remember that, but you can round, of course. Which of these is not like the other? Again, all you're trying to do here is match either a polyatomic or an ion with what it really is. Phosphate, PO4 3-. Yep, that is phosphate. We'll skip sulfate. Aluminum +3. This is the aluminum cation. Aluminum is in the 3rd period. It will form a +3 ion. Oxide, -2. Oxygen is in the 6th, so it will add 2 electrons and make it a -2. Nitrate, this is the parent for the nitrogens, NO3 with a -1. This is not per sulfate. Sulfate, you remember, is SO2 with a 2- charge.
And can you just read that one? Like if oh, never mind. I see.
Yep. Simple significant figures. How many do we have here?
4.
Step one, right, step one, you have a decimal point.
I'm saying
That
you.
means that leading zeros don't count, but trailing zeros do. So we have an 8 and 3 real zeros for 4 significant figures. How many significant figures here? Well, this is scientific notation, isn't it? Remember, in scientific notation, all the digits that are in the coefficient are significant. All of them. So this is 5 significant figures. And here we have a decimal that we're converting to scientific notation. First of all, we look at this, we have only leading zeros. So we're going to have 2 significant figures, right? Only 2. We're going to take and move our decimal from here to here. That's 7 places. And that's a negative coefficient. So we're looking for 2 significant figures and a 10 to the minus 7. I think that this one is what we're looking for. All right, let's do chlorine and do its electron configuration. Here's our periodic table. And chlorine lives right down here. Now, it's in the 3rd period, isn't it? What you need to remember is, because it's in the 3rd period, that means that period 1 and period 2 are full. They're already full. So, how many can we put in 1? Only 2 electrons. 1 up, 1 down. 2s, only 2. P's, we have 1, 2, 3, 4, 5, 6 p electrons, and we put them in pairs. Our 3s, we're over here, so 3s is already full. And now we have 1, 2, 3, 4, 5 electrons to go into the p orbitals. 5 electrons.
Got it wrong enough.
Put them
I
in,
got it wrong enough.
put them in, one at a time, with the same spin.
Down number 2.
But why you not putting them down? Up, down, up,
Oh
down?
yeah, I'm
Yes,
optimistic.
but you gotta do the ups first.
And the last 2 we'll put in an
4 and
opposite
5.
spin, like that. Any questions?
That's scared for a moment.
Well, let's try this with shorthand. And let's do carbon. Define carbon. Carbon's one of our friends here. Has an atomic number of 6. It's in the 2nd period. So that means the 1st period is full. Well, all of these have 1s2, so they're all full. Okay. We're over here in the P block. That means that the S is also full. So we're looking here for 2s with 2. So these guys all work nicely. And finally, over here in the P's, we have 1, 2 electrons. So that's going to be a P2. So, looks like this guy is the only one that works. All right, a physical change. And what is true? Our physical change is always accompanied by a change in state. No. Changes of state are physical changes, but there are other things you can do as well. Other physical changes you can do as well. Physical changes result in the formation of homogeneous mixtures, not new compounds. Well, no, there's lots of things you can do that don't make mixtures, right? Well, that's not right. They always produce developments. I don't think so. Doesn't make sense. A and C were both wrong. This is the dreaded none of the above.
So what is true regarding a physical change then? So what is true regarding a physical change then?
Well, it's you can change, say the not the density, the appearance of something. You can take a lump of gold and pound it out into gold leaf. That's a physical change with malleability, but it's still gold. Has it gone into a different element? It hasn't changed state. Here we have P2O5. What are we going to call this? Step 1. We have to decide, is this molecular or ionic? So the test you use. Does this have a metal in it? Look at our periodic table. Phosphorus is here, oxygen is here. These are both nonmetals. Okay? They're both nonmetals. That means it's going to be a molecular compound, and we're going to use multipliers. Right? All right. So, we have 2 phosphorus. Our multiplier for 2 is di. So we want to find a diphosphorus. We have 5 oxygens. The prefix or the multiplier for 5 is pent. So this is pent oxide. Looks to me like diphosphorus pentoxide should work. How many oxygen atoms in copper 2 sulfate? In order to do this, you have to be able to write down copper 2 sulfate and then count, right? Copper is a transition metal. That's why we have the copper 2. That tells you that the charge on copper is +2. Right? Now you say, what in the world is sulfate? Well, we remember sulfate from the previous slide. It was SO4 -2. So, sulfate is -2, and it looks like this. Copper is +2. So we simply need 1 + 2, 1 - 2. Now we need to be able to count to 4. 1 copper, 1 sulfate, 4 oxygen.
So the answer is C.
Another simple density calculation. We are given a density. What volume will 58.3 grams of a liquid occupy? Same thing like before. We know that density is mass divided by volume, right? Here we're solving for volume. If you take this equation and rearrange it, solving for volume, volume is equal to mass divided by density. So to get the volume, all you have to do is take our mass, 58.3, our density, 0.841, and divide them. When you do that, you get 69.3 mils. Again, we're working with 3 significant figures everywhere, so this works. On this exam, you will get to draw a Lewis structure. Yay! Let's practice with CO2. Step one, you look at your periodic table and you find your two elements. Here's carbon, here's oxygen. Carbon is in the fourth group, so it'll have 4 electrons. Oxygen is in the sixth, it will have 6 electrons each. So we simply arrange them. Carbon in the middle, with its 4 electrons, and each oxygen with 6. Now we can easily make a bond here, can't we? Bond here, no problem. But that would only give our carbon 2, 4, 6 electrons, wouldn't it? That's not enough. So what we're going to do is take one of these electrons, move it up, move one of these guys down, and we'll make a double bond. Right? So this is a double bond now. This carbon now has 1, 2, 3, 4, 5, 6, 7. In order to give it its 8, we're going to move this one up, move this one into here. And now the carbon has 8, and each oxygen also has 8. If we want it to be more contemporary, we can convert this into dashes, simply like that. And that is carbon dioxide. Any question?
Does it matter that, like, in what we,
Nope, doesn't matter where the electrons are, long as,
is 8 around?
yeah, they're right around it.
Now, never mind.
Let's do one a little bit simpler. In a properly drawn Lewis structure for ammonia, how many valence electrons are around the nitrogen? Well, nitrogen is here in group 7 or group 5. It has 5 electrons. Hydrogen is in group 1. It has 1 electron. So this is 5 electrons, and this is 1. Put our nitrogen in the middle, put the 3 hydrogens around it. And you should be able to see right away, we can make a nice bond here, nice bond, and a good bond there. Scooch them all together. And if you want, convert it to a dash drawing. Maybe. Nope, didn't convert. Well, obviously we would have 3 dashes here for our 3 hydrogens.
Okay, so what's the answer? I'm sorry. It would be 8, you said?
I'm sorry, what?
The answer is 8.
Oh yeah, I
Okay.
forgot to say the answer. 8 electrons, just like you would expect. All right, another nomenclature, K2O. What you ask yourself is, does this contain a metal? Look at our periodic table. There's K, group 1, it's a metal. This is ionic. If it's ionic, you don't use multipliers, right? So, with ionic nomenclature, all you do is list the cation and the anion. So, because it's in group 1, we don't need to show its charge. It's always 1. This is dipotassium, monoxide, dipotassium. Those are all wrong because we don't use the multipliers. One is right, obviously is simply potassium oxide. Oops. Potassium oxide. This projector, the yellow doesn't show up very well. In which of the following compounds will the cation be +3? Well, calcium. Look at your periodic table. Where's calcium? Right here in group 2. So it'll be a +2. Magnesium. By gosh, magnesium's also in group 2. And it's a +2. Ammonium. Remember, ammonium was our polyatomic. And it's a +1. Aluminum sulfide. Aluminum is here in group 3. Therefore, it will be a +3. And finally, phosphorus. Well, that's a non-metal. So that one's totally out anyway. Aluminum sulfide. Aluminum in group 3 with a +3 charge.
Bless you.
Thank you.